Hello, welcome to the session 2 on PN junction diodes. In this session, we are going to learn diffusion current, potential barrier across a PN junction, forward and reverse bias, and barrier height modification and depletion layer width modification after bias. As we saw in session 1, when a PN junction forms, there is a depletion layer near the junction, and the depletion layer will be depleted of moving charges. There will be charges in the depletion layer, but those charges are due to the presence of ions which are not capable of moving. So that region is like an insulator which cannot carry current, and the width of the depletion layer will depend on the concentration of the doping. So when we form a PN junction, the P region contains a large number of holes which are majority carriers, whereas N region contains lesser number of holes which are minority carriers. So the holes will move from high concentration region to low concentration region. That means from P to N across the junction. Similarly, electrons will move from N region to P region. That too will be across the junction. And this type of movement due to the concentration gradient is referred to as diffusion, and the current due to this movement is referred to as diffusion current. So even if we don't connect this P region and N region to a battery, there will be an initial current due to this diffusion. Whereas if we are connecting it to a battery, there will again be a current, and that current is referred to as a drift current. Drift is the movement of charge carriers in a potential field. So in this case, we haven't connected this to a battery, so the only current present is the diffusion current. And the diffusion current is given by the equation J. Here in this slide I have written JP. JP is the current density due to the movement of holes, and that will be the sum of drift current and diffusion current. Here we don't have drift current, so it is represented as the initial current is only due to diffusion, and that current density is given by negative of E dp by dx, where E is the charge of electrons. So here we are considering the current density due to holes, and we are using the charge of electrons, and that's why there is a negative sign over here. Whereas if you are writing instead of E, if you are writing P, which is the charge of holes, then there will be a positive sign here instead of a negative sign. So anyway the diffusion current is due to the holes. Jp is equal to negative of E is the charge of electrons, and capital dP, which is a constant related to the diffusion of holes, which is referred to as the diffusion coefficient, and dP by dx is the concentration gradient of holes, or how the concentration of the holes vary with respect to x. So this equation represents diffusion current. So the formation of a depletion region is shown in this diagram once more. In the P side near the junction we have got stationary negative charges, and in the N region near the junction we have got stationary positive charges. So those formation of those depletion region is due to the movement of charge carriers across the junction. They recombine with the opposite charges and they will disappear. So that region is depleted of moving charges, so that's not capable of conducting any current. So that means when the depletion region has been formed, the diffusion current which was initially present, that current will stop. So that is what is shown here in a different way. We explained this phenomenon due to the presence of something called potential barrier. So that is shown here, and you are familiar with what is potential. Potential at a point is the work done in moving unit positive charge from infinity to that point. So here what we are going to see is, we will assume that this p region and n region both are uniformly doped. So that means if you take any point in the p region, that will be having a particular potential, and every point in the p region is assumed to be in the same potential due to uniform doping. So we what we are going to do is, we have got the p region which is at a particular potential, a constant potential, and n region is at a different constant potential. So that is what is shown in the diagram C over here. You have got this graph. C is the potential as a function of x. X is the distance from left to right. So the p region is shown to be at constant potential using this red color graph. It is at constant potential, and n region is also shown to be at constant potential, and in this diagram it is shown to be higher than the potential in the p region. And in between you have got the depletion region, which does not carry any charge. So that means from p region to n region there is a gradual variation in potential, and that is that's the meaning of this graph in C. And the blue arrow which is shown here in the graph C, and it is represented as VD. It is the potential difference between the p region and the n region, and it is indicated by the symbol VD, and that is referred to as the potential barrier. So why the diffusion current, which was initially present, why does it stop once when the potential barrier has been formed, or the depletion region has been formed, is explained as due to the formation of potential barrier. So that means the charge carriers will now have to jump across over the barrier in order to make a current. So if they do not have enough energy to cross that barrier, they are not going to be successful in making current, and that's why this diffusion current stops. So that's why when you take a diode from the lab, you know it is a p-n junction diode. The potential barrier is present, and you cannot expect to have a diffusion current, because diffusion current is present only in the beginning stage. Once when it becomes stable, once when you have got a depletion region formed, and once when you have got a potential barrier formed, you cannot expect to have diffusion current there. So the same thing is drawn in a different manner in this diagram, because the difference between the previous diagram and this diagram is, you focus on the topmost diagram. It is a graph, and you look at the graph which is indicated using red line. Here this is actually the constant high potential in the p region, and on the other side in the n region you have got a constant low potential, and whereas the blue graph is the reverse of that. You have got a constant low potential in the p region and high potential in the n region. That is because you can either use draw this graph with respect to holes or with respect to electrons. For example, if the red graph is with respect to holes, that means you are assuming the work that you have to do in order to bring a unit positive charge and place it at the p region. So p region already contains a lot of positive charges, so it will be resisting the incoming hole. So that means you will have to do a lot of work, and that is why this is shown to be at a high potential than the potential if it is drawn with respect to holes in the n region also. Whereas if you are drawing that graph with respect to electrons on the n side will resist the movement of incoming electrons, so that will be represented as having a high potential. So anyway, you can make use of any one of these. Normally we draw this graph with respect to holes, so I think it is nice to draw it like the red color graph over here. But anyway, it indicates that you have got a constant potential in the p region and another constant potential in the n region, and the difference between these two is the potential barrier. So when the depletion region and the potential barrier has been formed, the diffusion current will stop. Now if you want to make current flow again through the circuit, what you have to do is, you will have to connect this diode to an external battery. So that is referred to as bias. There are two ways in which you can give bias to a PN junction diode, and this is referred to as, this is the diagram which shows the way in which you can give forward bias. In the case of forward bias, the P region is connected to the positive of the battery and N region is connected to the negative of the battery. So when we do this, the charge carriers are now capable of moving. For example, if you consider the electrons on the N side, they are connected to the negative plate of the battery. So those electrons will be repelled due to the presence of the negative charge on the battery and will move away. So that means they will move into the depletion region. So previously there were no moving charges in the depletion region, but now when we have given forward bias, due to the presence of the battery, the charge carriers will be injected into the depletion region. From N region electrons will be injected into the depletion region, and from P side holes will be injected into the depletion region. So that means now they are capable of crossing the potential barrier and they will make a current. So that means you can say when you are giving a forward bias, it's like since the electrons are moving from N region to the depletion region and holes are moving from P region to depletion region, that is essentially narrowing down the depletion region. So when the depletion region gets narrowed down, the height of the potential barrier is also reduced. So that is what is happening in forward bias. Depending on the potential in the battery, you can, for example, at a low potential, the barrier height will be reduced to a small extent. If you are giving high potential, the barrier height will be reduced to a larger extent. So that means now the charge carriers are finding it easy to cross the potential barrier, reach the other side, and they can make a current. So when you have given forward bias, that will enable the current to flow through the circuit. That is what is shown in this animated picture here. Here you can see on the left side you got the diagram in which you can see the charge carriers are moving, and when they are moving they cross the junction and they make a complete circuit and it makes a current. So in this case on the left hand side, this is drawn for two different values of the battery potential, for 0.6 and also for 1 volt, 0.6 volt and for 1 volt, and correspondingly on the right side you have got a graph which is actually the VI characteristics, and the current corresponding to 0.6 volt and 1 volt is shown using an orange dot. So what you have to focus what you have to pay attention in this diagram is you have got a PN junction and there is a change in depletion layer width when you are connecting battery. For example, when the battery voltage is 1 volt, see here you can see the potential barrier height is narrow, whereas now it has become larger when the potential is 0.6. So correspondingly at 1 volt you have got a high current near 200 milliampere, and when it is 0.6 the current is very low at 1 milliampere. So this is actually what we call the forward bias. So due to forward bias, the height of the potential barrier will reduce and the width of the depletion layer is also narrowed down. And the second type of bias is reverse bias. In this case, the P region is connected to the negative of the battery and N region is connected to the positive of the battery. So here for example, if you examine the P region, the holes are connected to the negative of the battery, so they will be getting attracted towards the negative plate. So that means they will try to move towards the battery, towards the N side, which means they will try to move further away from the depletion region. Similarly, electrons in the N side will move away from the depletion region and they will try to move towards the positive of the battery. So that means essentially in the PN region, the charge carriers are moving further away from the depletion region. So that means the depletion region will get wider and wider depending on what is the voltage which is used in the battery. So that will make the movement of the charge carriers across the junction will become more and more difficult. Or we can say, when we give reverse bias, two things will happen: the depletion region will get wider and the potential barrier will become taller. So that means there is no current in reverse bias. So there are two simple ways in which you can represent forward bias and reverse bias. In the case of a real diode, it is shown here. On the left side, it is forward bias. Here, for when you have forward bias, there will be some current flowing through the circuit. So this is what is shown in the diagram below. Below the diode, you have got at the top side you have got a diode which is forward biased, and in the bottom side you have got another diagram, and that diagram below that diode is referred to as the equivalent circuit. So on the left side you have got the equivalent circuit for forward biased real diode, and on the right side bottom you have got the equivalent circuit of reverse biased real diode. So I will explain in the case of forward bias, what we have is you have got current flowing through the circuit when you are giving forward bias. So that means it is essentially equivalent to a closed circuit or closed switch. So the two red black dots which are shown, that represents the switch, and when you have got an arrow connecting those two, a bar connecting those two, it will represent a closed switch, and that closed switch is connected to a battery of voltage 0.7. 0.7 is actually the potential barrier. So that means when you have a diode in forward bias, it will make a current, but in order to make a current, the charge carriers will first of all cross the potential barrier, and in order to do that, whatever is the potential barrier, that much is utilized. For example, if you are connecting the battery, the diode to a battery of 10 volt, out of that 10 volt, if 0.7 is the potential barrier, 0.7 will be used in crossing over the barrier. So 10 minus 0.7, only 9.3 volt will be successful in making current. So that is why we are showing in the equivalent circuit, we are showing an additional battery. That battery is drawn in such a way that the positive of the battery is on the same side as that of the P region, and negative of the battery is on the same side as that of the N region. So this is referred to as the equivalent circuit of forward biased real diode. If it was an ideal diode, we will assume that there is no potential barrier, so you don't have to draw the 0.7 volt battery, you just have to show it using a closed switch. On the other hand, when your diode is reverse biased, there is no current, so it is essentially equivalent to an open switch. So that's why the switch is shown to be open there. And in order to show the potential barrier, actually you don't have to show the potential barrier there, because we don't use up that much voltage in order to cross the barrier, so that there is no point in showing the battery of 0.7 voltage there. But in order to make it similar to the previous diagram, 0.7 is shown here. It doesn't matter even if you omit this 0.7 when you draw the equivalent circuit of reverse biased PN junction. So in this diagram, I have tried to sum up what is happening to the PN junction under forward biased and reverse biased conditions. So I am showing 3 diagrams. First one is unbiased. You have got a P region and N region, and a depletion region of moderate width, and a potential barrier of moderate height. And when you give forward bias, you can see that the depletion region has become narrower, and the potential barrier has become shorter, or the height has become smaller. Whereas when you are giving reverse bias, the potential barrier has become larger, and the depletion region has become wider. So, in order to sum up this session, what we have learned so far is during the p-n junction formation, there is an initial diffusion current, and this diffusion current will stop when the depletion region and the potential barrier form. And forward bias can reduce the width of the depletion region and height of the potential barrier, whereas reverse bias will increase both of them. Forward biased p-n junction is analogous to a closed switch, and reverse biased p-n junction is similar to an open switch. So coming up in session 3, we will see more details of the circuit of forward and reverse biased p-n junction. We will see how we can study or we can draw the VI characteristics by connecting the diode to a suitable circuit in such a way that we will be able to change the voltage and measure the corresponding current. So you know that if you are given a constant voltage battery, how you can take, for example, you'll have to initially begin with 0 volt and then gradually increase the volt, and then you'll have to measure the corresponding current and draw a graph for various values of V. So that is what we call the VI characteristic. So essentially in the experiment you will have to take the measurement of current for different values of V, but you will be given a constant potential battery. So in such a situation, how will you be able to take different potential from a constant voltage battery? You know that in that case you can use rheostat. So that is what we are going to see, how we can connect the circuit in order to study the forward and reverse characteristics. And then in the next session we will also see the basics of a special diode which we call the Zener diode. So long you can next class we may try to solve some problems related to this topic. You can go through. So far we haven't discussed any equations except diffusion, but there are some equations which you are familiar with, so revise. And if you have got questions, you post it in the group and you can mail me, so I'll try to answer them. So see you in the next session.